Sunlight touches your skin every single day. It travelled 93 million miles in just 8 minutes. But for that beam of light, the clock never moved. 0 seconds passed on its journey. You're older right now than the light warming your face. Light cannot age anywhere in the universe, ever. Today we chase starlight born from dead stars, follow a beam trapped forever circling a black hole, and stand at the edge of the visible universe where galaxies disappear beyond light's own speed limit. If mysteries like this excite you, hit subscribe and stay with us. Take a breath. We begin now. Look up at the sun for 1 second, then look away. That flash you just saw left the sun 93 million miles away, and it took 8 minutes to reach your eyes. That gap is proof that light needs time to travel, the same way sound needs time to cross a stadium before you hear the crowd roar. But here is the strange part. While 8 minutes pass for you, 0 seconds pass for the light itself. Picture a school bus driving from Los Angeles to New York. For the passengers, the trip takes 4 days. For someone standing on a bridge watching it pass underneath, that same trip also takes 4 days. Everyone agrees on the time. Light breaks that agreement completely. If you could somehow ride on a beam of light from the sun to your eye, your personal stopwatch would never move. Not one tick. The moment light leaves the sun and the moment it lands on your skin would happen at the exact same instant, according to the light. Scientists have tested this idea for over a century, and it holds up every single time. It comes from Albert Einstein's theory of relativity, one of the most carefully checked ideas in all of physics. The faster something moves, the slower time passes for it. Light moves at the fastest possible speed, 186,000 miles per second. Push that speed to its absolute limit, and time stops moving at all. That means every photon of sunlight touching your face right now has existed, from its own point of view, for 0 seconds. It was born in the sun's core and died on your skin in the same breath, even though you experienced 8 full minutes in between. Now stretch that idea further. The North Star sits about 430 light years away. The light hitting your eyes tonight left that star centuries ago, back before the United States was even a country. For you, 430 years passed. For the light, nothing passed at all. It arrives exactly as young as the moment it was born. This single fact rewrites everything about how you should picture starlight. Every beam hitting your eyes tonight, whether it travelled 4 minutes or 4 billion years, experienced none of that time. 0. From light's point of view, the entire universe collapses into a single instant flash. Try picturing it like a photograph instead of a movie. A photograph has no motion, no ticking clock, no next moment waiting to happen. It is one frozen slice of time, complete on its own. That frozen photograph is close to what existence looks like for a beam of light. There is no in-between. There is only the instant it leaves and the instant it lands, pressed together as if the miles and the years never happened at all. It sounds like it breaks the rules of common sense, and it does. Nothing in your daily life prepares you for a universe where distance and time bend depending on how fast you move. A car, a plane, even a rocket ship all obey the rules you grew up with. Light plays by a different set of rules entirely, rules first imagined by a teenager staring out a classroom window, wondering what it would feel like to chase a beam of light across the sky. That daydream would grow into one of the strangest ideas humanity has ever proven true. A 16-year-old boy sat in a classroom in Switzerland, barely listening to his teacher. His name was Albert Einstein, and his mind was somewhere else entirely. He was imagining himself running alongside a beam of light, matching its speed exactly, like a kid racing a bicycle next to a moving train. If he could somehow catch up to light and travel right beside it, what would he see? Would the light freeze in place next to him, like a wave stuck in midair? That single daydream dreamed up by a bored teenager would eventually crack open the deepest secrets of the universe. At first, the idea seems harmless. You chase a car, you eventually catch it, and it looks parked next to you. Chase a light beam the same way, and logic says the same thing should happen. The light should appear frozen, its waves standing still in space. But Einstein kept running into a wall. Nothing in nature allows a wave of light to simply stand still. Light without motion is not light at all. It has no meaning, no existence, so something else had to give. Years later, working as a patent clerk far from any university lab, Einstein returned to that same question. He realized the problem was not with light. The problem was with the very idea of catching up to it. No matter how fast you travel, whether in a car, a jet, or a future spaceship, light always moves away from you at the exact same blistering speed. You can never close the gap. You can never ride alongside it. You can never make it stand still. Picture chasing a shadow cast by a flashlight. No matter how fast you sprint, the shadow always stays exactly the same distance ahead, sliding away as fast as you approach. Light behaves the same way, except it does it for a reason built into the fabric of space and time itself, not just a trick of light and shadow. This meant something had to bend to keep light's speed constant no matter who was watching or how fast they moved. Einstein discovered that space and time both had to stretch and shift together, like two dancers moving in perfect sync to keep the music from ever-changing tempo. Moving clocks tick slower, moving rulers shrink shorter. All of it happens automatically, secretly, correcting itself so that light always wins the race by exactly the same amount. A teenager staring out a window had stumbled onto one of the strangest truths in physics, simply by refusing to accept an answer that felt half-finished. He spent the next 10 years turning that daydream into equations that would reshape astronomy, engineering, and even the satellites orbiting above your head right now. Think about how strange that is. Everything else in your world adds up normally. Throw a baseball forward from a moving truck, and it flies faster than a ball thrown from a truck parked still. Speeds add like simple addition. Light refuses that math. Add any speed you want to light, even the speed of the fastest rocket ever built, and light still moves away at the exact same 186,000 miles per second. The chase that could never be won became the foundation for understanding why light itself can never grow old. But proving that chasing light was truly impossible took more than imagination. It took an experiment, built with mirrors and beams of light, designed to catch nature in the act. A rocket engineer once said that with enough fuel you could reach any speed you want. That statement is wrong, and the reason why reveals one of the strangest walls in the entire universe. No matter how much fuel you burn, no matter how powerful your engine, nothing with mass can ever reach the speed of light. Not almost, not close. Never, under any circumstance, at any point in the future. Here is why. Mass and energy are linked together, tied by Einstein's famous equation. As any object with mass speeds up, it gains energy, and that energy behaves exactly like extra mass. The object effectively gets heavier the faster it goes. A spaceship near light speed would weigh dramatically more than the same spaceship sitting still on a launch pad. The closer you push toward light speed, the heavier the ship becomes, and the harder your engines have to work just to add a little more speed. Double the fuel, and you might expect double the speed. Instead, most of that extra energy goes into extra weight, not extra motion. Picture pushing a shopping cart across a parking lot. At first, it is easy. A gentle push sends it rolling smoothly. Now imagine that same cart magically gaining 1,000 extra pounds every second you keep pushing it. Eventually, no amount of muscle could budge it another inch. That is what happens to any spaceship approaching light speed. Its effective mass balloons toward infinity, and pushing it even slightly faster would require infinite energy. More energy than exists in the entire universe. This is not a limit of current rocket technology. Engineers cannot simply invent a stronger engine someday and break through it. The wall is built into the laws of physics themselves, discovered through decades of experiments in giant particle accelerators. Scientists have taken tiny particles like electrons and protons, particles thousands of times lighter than a single grain of sand, and pushed them with tremendous amounts of energy. Those particles get remarkably close to light speed, 99.9% and beyond, yet they never fully arrive. Every accelerator on Earth confirms the same unbreakable limit. Light itself avoids this problem entirely, for one simple reason. Light has no mass at all. A photon weighs nothing, so the equation that traps every rocket, every particle, and every material object in the universe simply does not apply to it. Light does not need to accelerate up to its top speed. It is born already moving at full speed the instant it is created, and it can never slow down or speed up from that number. This single fact splits the universe into two categories forever. Anything with mass, from a spaceship to a speck of dust to your own body, is permanently trapped below light speed, no matter how much energy you throw at it. Anything without mass, like light itself, has no choice but to always move at exactly that speed, never faster, never slower. That divide explains why a beam of light can never grow old, while everything else in the universe does. But knowing the wall exists is different from proving it. Decades before rockets or particle accelerators existed, two scientists built a machine using nothing but mirrors, hoping to catch light breaking its own rules. In a basement laboratory in the 1880s, two American scientists built a machine designed to catch the universe cheating. Albert Michelson and Edward Morley believed that light needed something to travel through, an invisible substance filling all of space called the ether. If Earth was constantly moving through this ether while orbiting the Sun, then light should travel slightly faster in one direction and slightly slower in another, the same way a swimmer moves faster with a current than against it. Their machine, built to detect that tiny difference, was one of the most precise instruments ever created up to that point. The device split a single beam of light into two paths, sent them off at right angles to each other, then bounced them back together using mirrors. If the ether existed, the two beams would arrive back home at very slightly different times, creating a pattern the scientists could measure with incredible precision. They tested it facing every direction. They tested it in different seasons, as Earth moved to different points in its orbit around the Sun. If there was even a whisper of a speed difference, this machine would catch it. The results stunned everyone involved. No difference showed up. None at all. The two beams of light arrived back together in perfect sync every single time, no matter which direction the machine faced or what time of year it was. Light moved at exactly the same speed in every direction, as if Earth were not moving through anything at all. Scientists at the time called it the most famous failed experiment in history, because it failed to find the one thing it set out to prove existed, and that failure ended up teaching the world something far bigger than success ever could have. Picture stepping onto a moving walkway at an airport, then noticing that walking forward, backward or sideways on it makes absolutely no difference to your speed. That is how strange this result felt to scientists at the time. It broke every expectation built from centuries of studying waves in water and sound in air. For years, the experiment left physicists confused, convinced something in their instruments must be wrong. It took Einstein, working independently, to explain what the failed experiment actually meant. There was no ether. Light did not need a current to swim through. Its speed was simply, permanently fixed, 186,000 miles per second, the same for every observer everywhere, no matter how fast that observer was moving or in what direction. That single idea became one of the two pillars holding up his entire theory of relativity. Scientists have repeated versions of this experiment for over a century since, using lasers, satellites, and instruments thousands of times more sensitive than the original mirrors. Every single test agrees. Light's speed never changes, not by a single mile per hour, regardless of who measures it or how fast they are moving while they do it. This fixed, unbreakable speed becomes the anchor for everything strange that follows. If light's speed can never change, then something else in the universe has to bend instead to keep the math working out. That something else turns out to be time itself, ticking differently depending on how fast you move, a discovery that leads straight to the strangest clock ever imagined. Imagine a clock built from nothing but a single beam of light bouncing between two mirrors. Light leaves the bottom mirror, travels straight up, hits the top mirror, and bounces back down. Each round trip counts as one tick. Simple, precise, and perfectly steady as long as the clock sits still. Scientists use this exact idea, called a light clock, to explain one of the strangest consequences of light's fixed speed. Now put that clock on a train moving at incredible speed. From the point of view of someone standing on the train, nothing changes. The light still bounces straight up and straight down, tick after tick exactly like before. But picture watching that same train speed past you from a platform outside. From your point of view, the light beam has to travel diagonally, since the train is carrying it forward the whole time it bounces. Here is the part that breaks everyone's brain the first time they hear it. Light speed never changes, no matter who is watching, remember? So if the beam on the moving train has to travel a longer diagonal path, but its speed stays exactly the same, then completing one tick must take longer, according to you on the platform. The clock on the train, from your outside point of view, ticks slower than a matching clock sitting still beside you. This is not an illusion caused by distance or eyesight. It is a real difference in how fast time itself passes. The faster something moves, the slower its clock ticks compared to someone standing still. Push a light clock close enough to light speed, and its ticks would stretch out almost forever, according to an outside observer. Now take this idea to its absolute extreme. What happens to a clock built from light itself, already travelling at the maximum speed the universe allows? The zigzag path becomes infinitely long. The gap between one tick and the next stretches out to infinity as well. In plain terms, the clock never ticks again. Not once. From the outside universe's point of view, time for that beam of light has completely stopped. This is exactly why a photon experiences zero time between the moment it is born and the moment it strikes something and disappears. It is not a rounding error or a tiny effect too small to notice. It is the mathematics of light speed taken all the way to its natural conclusion. Light does not experience time slipping by slowly. It experiences no time slipping by at all. Physicists have a specific name for this personal onboard time, measured by a clock travelling along with something. They call it proper time. For every rocket, every planet, and every person, proper time ticks forward, slower or faster depending on speed, but always moving. For light, proper time freezes completely, locked at zero forever. A beam of a light in the truest sense has no experience of its own journey at all. It has no story to tell about the miles it crossed or the years that passed along the way. But everything around that beam of light, every clock, every calendar, every human life it passes by, keeps ticking the entire time, second after second, year after year, completely indifferent to the frozen silence inside the light beam itself. And that difference is about to get far stranger. A pilot's watch and a watch left behind on the ground will never agree again. Not by much, but never by zero either. This is time dilation, and it applies to everything that moves, from cars to rockets to planets, well beyond beams of light alone. Speed itself slows down time. The faster an object travels, the slower its clock runs compared to a clock that stayed still. Time itself genuinely passes at a different rate depending on how fast you're moving through space. No malfunctioning clock or dying battery involved. At everyday speeds, like a car on the highway, or even a jet crossing the country, the effect is so small it takes incredibly sensitive instruments to detect it at all, a difference measured in billionths of a second. You would never notice it in your entire lifetime, but the effect is real, and it grows dramatically larger the closer something gets to the speed of light. Picture two friends. One stays home, the other boards a spaceship capable of reaching 70% of light speed and takes a long journey through the solar system before returning. When the traveller steps off the ship, their watch shows less time has passed than the watch of the friend who stayed home. Time genuinely moved slower for everything aboard that ship, including the traveller's own heartbeat, their own thoughts, every atom in their body ticking along at a delayed pace compared to Earth. The watch itself worked perfectly the entire trip. This sounds like something from a movie, but engineers deal with it as a real, practical problem every single day. Satellites orbiting Earth move fast enough that their onboard clocks tick at a noticeably different rate than clocks on the ground. If left uncorrected, that tiny mismatch would snowball into major errors within hours. Every piece of technology, depending on precise timing, has to account for this stretching and shrinking of time caused by speed. Here is a comparison that helps. Imagine walking through a swimming pool versus walking on dry land. On land, you move freely at full speed. Wade into the pool, and the water resists you, slowing your steps no matter how hard you push. Speed through space works a little like that pool, except instead of slowing your legs, it slows your clock. The faster you move through space, the more your personal time gets dragged down, resisting the normal flow that people standing still experience. Push this idea all the way to its limit, the speed of a light itself, and the resistance becomes total. Time stops completely. This is the same conclusion reached by the light clock, arriving now from a completely different angle. using nothing but the physics of everyday moving objects, from cars to satellites to spaceships. Time dilation is not a rare exotic effect saved only for beams of light. It is a universal rule, quietly shaping every clock, every heartbeat, and every phone in your pocket, whether you notice it or not. Astronauts aboard the International Space Station experience this for real, aging a tiny fraction of a second less than everyone on Earth. By the time they return home, a measurable gap caused entirely by their orbital speed. And nowhere is that hidden influence more surprising than in the satellites, silently circling above your head right now, correcting for a stretch in time that most people will never know exists. Somewhere above your head right now, a satellite is quietly correcting for a problem Einstein predicted more than a century ago. Your phone's GPS works by talking to a group of satellites orbiting roughly 12,000 miles above Earth. Each satellite carries an incredibly precise atomic clock, and your phone calculates your exact location by timing how long signals take to arrive from several satellites at once. Even a tiny timing error creates a location error, since light and radio signals travel so fast that a difference of just 1 second is worth about 186,000 miles. Those satellites move fast, circling Earth at roughly 8,700 miles per hour. At that speed, time dilation kicks in. Their onboard clocks tick slightly slower than identical clocks sitting still, down on Earth's surface, exactly as Einstein's theory predicts. Left alone, this effect alone would cause GPS clocks to lose about 7 microseconds every single day. That sounds tiny, but in the timing world of GPS, it is enormous. There is a second effect working in the opposite direction, caused by gravity instead of speed. Satellites orbit far above Earth, where gravity pulls much weaker than it does down on the surface. Weaker gravity means their clocks actually tick faster than ground clocks, adding about 45 microseconds of gain every day. Add both effects together, the slowing from speed and the speeding up from weaker gravity, and satellite clocks run about 38 microseconds, faster than ground clocks every single day. 38 microseconds might sound impossibly small, smaller than the blink of an eye by thousands of times. But left uncorrected, that tiny daily drift would snowball fast. Within just 1 day, GPS location errors would grow by about 6 miles. Within a week, the system would become almost useless, placing you on the wrong street, in the wrong neighborhood, possibly in the wrong city entirely. Engineers solve this by building the correction directly into the satellites themselves. Before launch, technicians deliberately tune each atomic clock to tick slightly slower than normal, cancelling out the predicted relativistic drift before the satellite even reaches orbit. It is a strange kind of tribute, a piece of hardware built and tuned specifically around a prediction Einstein made, using nothing but chalk, a blackboard, and pure imagination, decades before satellites or GPS existed. The next time your phone pinpoints your exact location on a map in under a second, that accuracy depends entirely on correcting for the fact that time itself moves at different speeds depending on how fast you travel and how strong gravity pulls where you're standing. Every rideshare pickup, every turn-by-turn direction, every dot on a map is quietly powered by relativity. Every single GPS satellite launched carries this correction, built directly into its design, a permanent working monument to a theory once dismissed by many scientists as pure imagination, decades before anyone imagined a device in every pocket depending on it. If satellites moving at a modest 8,000 miles per hour create a measurable, correctable drift in time, then a far stranger question follows naturally. What happens to something moving not thousands of miles per hour, but hundreds of millions of miles per hour, raining down from space every single second, completely invisible to the human eye? Right now, tiny particles are raining down through your body, born from collisions happening high above your head. These particles are called muons, created when cosmic rays from deep space slam into Earth's upper atmosphere, about 40 miles above the ground. Each collision creates a spray of muons that immediately begins racing toward the surface at close to the speed of light. There is just one problem. Muons do not live very long. Left alone, a muon survives for only about 2 millionths of a second before it breaks apart into other particles. Do the simple math, and something strange shows up immediately. Even moving at nearly light speed, a muon with a 2/millionth of a second lifespan should only travel about 2,000 feet before disintegrating. That is roughly the height of a very tall skyscraper, nowhere close to covering the 40 miles between the upper atmosphere and the ground. By ordinary logic, almost no muons created up there should ever reach a detector down here, except they do. Scientists placed detectors at mountaintops and at sea level, and counted muons arriving at both locations. Enormous numbers of muons survived the entire 40-mile journey, striking detectors on the ground in huge quantities, far more than simple math without relativity would ever predict. This became one of the clearest, most direct proofs of time dilation ever recorded using nothing but naturally occurring particles falling out of the sky. Here is the explanation. From Earth's point of view, the muon is moving so close to light speed that time dilation dramatically stretches its lifespan. A muon that should live for 2/millionths of a second, according to its own internal clock, appears to survive roughly 10 to 20 times longer from our point of view on the ground. That stretched lifespan gives it more than enough time to cross the entire 40-mile journey before finally breaking apart. Flip the perspective around, and an equally strange explanation appears. From the muon's own point of view, its lifespan never changes at all. It still only lives for 2/millionths of a second, exactly as expected. Instead, the muon experiences the 40 miles of atmosphere as dramatically compressed, shrunk down to a tiny fraction of its normal length, thanks to a partner effect of relativity that squeezes distance the same way time gets stretched. Either way you explain it, stretch time or squeeze distance, the muon survives the trip, and both explanations agree perfectly on the final result. Picture a marathon runner who normally could only run half a mile before collapsing from exhaustion, somehow finishing an entire 26-mile race because the world briefly compressed itself into their favour. That is roughly what happens to a muon, born in the upper atmosphere and detected safely on the ground below, a trip that should be physically impossible without relativity bending both time and distance in its favour. This is not a rare laboratory experiment locked away behind university walls. Muons are raining onto every square mile of Earth's surface every single second, undeniable proof written across the sky of a universe where time bends depending on how fast you move. Right now, as you listen to this sentence, thousands of these tiny time travelers are passing harmlessly through your body, each one carrying proof of relativity that most people will never think twice about. Two twins say goodbye at a launch pad. One boards a rocket bound for a distant star, the other stays home, waving until the rocket disappears from view. Years later, the travelling twin returns, only the reunion does not look like anyone expected. The twin who journeyed through space at close to light speed has aged only a few years. The twin who stayed on Earth has aged decades. Same starting age, same birthday, completely different amount of time passed for each of them. This is the twin paradox, one of the most famous thought experiments to come from Einstein's theory of relativity. It sounds like a plot hole at first. If motion is relative, meaning either twin could claim they were the one standing still while the other moved, then shouldn't each twin expect the other to have aged less? That confusion is exactly why it earned the name paradox. The resolution, though, removes the contradiction completely. Here is the key detail: only one twin actually changes direction. The travelling twin accelerates away from Earth, at some point turns around, and accelerates back home again. The twin who stayed on Earth never changes course at all, remaining in one smooth, uninterrupted path the entire time. That difference, acceleration versus no acceleration, breaks the symmetry between them and settles the question of who actually aged less. The traveller, not the twin who stayed home. Picture two people walking across a giant park, both aiming for the same tree on the far side. One walks in a perfectly straight line the whole way. The other wanders off at an angle, changes direction part way, and eventually meets back up at the same tree. Even though both people end up in the same place, the wandering walker crossed more total ground to get there. Something similar happens with time itself during the twin paradox, except instead of physical distance, the travelling twin crosses less total time, precisely because of that change in direction. Scientists have tested a real version of this experiment using atomic clocks instead of actual twins. In 1971, researchers flew extremely precise atomic clocks aboard commercial airplanes, circling the globe in both directions, then compared them against a matching clock that stayed on the ground the entire time. The airborne clocks came back showing a measurable, predictable difference from the stationary clock matching Einstein's equations almost exactly. A version of the twin paradox tested with real machines instead of imaginary astronauts, and relativity passed the test perfectly. Now push the twin paradox to its most extreme possible version. Imagine, instead of a twin travelling at 70% of light speed, something travelling at exactly light speed itself, a photon. A photon leaves its source, crosses the entire visible universe if nothing stops it, and never turns around, never ages, never experiences a single tick of its own personal clock along the way. The twin paradox shows that speed alone stretches time dramatically. Push that same idea to its absolute limit, and the traveller's clock freezes entirely, matching exactly what happens to every beam of starlight crossing the emptiness of space between you and the night sky above. Every twinkle overhead is, in a sense, a twin that never came home, still frozen at the exact age it was the instant it departed. Somewhere in the southern sky sits a star system, just 4 light-years away, close enough that its light left home during your own lifetime, and far enough to remind you how enormous even the smallest cosmic distances truly are. Alpha Centauri is the closest star system to our own Sun, and light from it takes about 4 years to reach Earth. That means the light entering your eyes tonight, if you could spot it, left that star system around 4 years ago. Whatever happened there 4 years back, whatever moment that light captured, is exactly what you would see tonight, frozen in transit the entire time. 4 light-years sounds close on a cosmic scale, and compared to the rest of the universe, it truly is. But translate that distance into something more familiar, and the scale becomes staggering. 4 light-years equals roughly 24 trillion miles. Driving that distance in a car at highway speed, without ever stopping to rest, refuel, or sleep, would take over 40 million years to complete. Light crosses that same unimaginable distance in just 4 years, a difference that shows exactly how blisteringly fast light truly moves, even while still taking real, measurable time to arrive. Here is where the earlier lesson about light's own personal clock returns, more powerful than ever. For you, watching from Earth, 4 years passed while that light crossed the gap between the two star systems. For the light itself, exactly 0 seconds passed. Not a fraction of a second, not the tiniest sliver of time. The light left Alpha Centauri and arrived at your eye in what amounts to the very same instant, according to its own internal experience, even though an entire 4-year gap separated those two events from your point of view on Earth. Picture mailing a letter that takes 4 years to arrive, only the letter itself experiences the delivery as happening the exact same moment it was dropped in the mailbox. That is the strange gift and curse of light-speed travel. Time completely disappears from the traveller's side of the story, while the outside world keeps marching forward at its normal pace the entire time. This creates a strange kind of built-in time machine, one that works constantly, without anyone building or operating it. Every time you look at Alpha Centauri, you're not seeing it as it exists today. You're seeing a 4-year-old snapshot, carried across the emptiness of space by light, that never aged a single moment along the way. If something dramatic happened at Alpha Centauri today, an explosion, a shift in brightness, anything at all, nobody on Earth would know for another 4 full years, the exact time it takes for that news, carried entirely by ageless light, to finally arrive. And Alpha Centauri is practically Earth's next-door neighbour, cosmically speaking. Stretch that same idea out towards stars far more distant, and the gap between when something happens and when humanity finally witnesses it grows from a handful of years into centuries, then thousands of years, then far beyond anything a human lifetime could ever measure. Somewhere overhead tonight sits a star whose light left home before your grandparents were born, and this is only the beginning of how far back that light can reach. Point at the North Star tonight, and you might be pointing at a ghost. Polaris, the star sailors and hikers have used for centuries to find true north, sits about 430 light-years away from Earth. That means the light reaching your eyes tonight left that star around 430 years ago, long before the United States existed, back when explorers were still mapping unknown coastlines using nothing but the stars themselves. Whatever you see when you look at Polaris tonight is not the star as it exists today. It is a snapshot from centuries in the past carried across space this entire time. Here is the unsettling part. Stars are not permanent, Every star eventually runs out of fuel, and depending on its size, it can swell up, collapse, explode, or quietly fade away. There is no way to know, just by looking, whether Polaris is still shining exactly as it appears tonight, or whether it changed dramatically, or even stopped existing entirely, sometime within the past 430 years. The star could have gone through violent changes we know nothing about, and we would not find out until light carrying that news finally makes the long journey to Earth. Picture receiving a text message that took 430 years to arrive. Everything in that message would be true the moment it was sent, but wildly out of date the moment it finally reached you. Every single star you see at night works exactly like that delayed message. Some barely a few years old, others carrying news from thousands or even millions of years in the past. Astronomers deal with this constantly. When studying distant stars, they are never observing the present. They are always looking backward through time, piecing together a kind of cosmic history book, using nothing but ancient light. A telescope functions as a time machine, letting scientists peer directly into the past simply by looking far enough away. This raises a strange and slightly dizzying question. Is Polaris right now, in this exact moment, still a normal, stable star? Almost certainly yes, since stars typically live for millions or billions of years, and 430 years barely counts as a blink in a star's lifetime. But for stars much closer to the end of their lives, that certainty disappears completely. Astronomers have genuinely wondered whether certain aging, unstable stars might have already exploded, with humanity simply waiting, unaware, for the delayed light of that explosion to finally arrive. Every constellation in the night sky is, in a very real sense, a patchwork quilt stitched together from light of wildly different ages, arriving from wildly different points in the past, all overlapping into a single picture at once. Some of those pinpricks of light left their source recently. Others left before recorded human history even began. Standing under a clear night sky means staring directly into layers of the past, stacked invisibly on top of each other, arriving all at once as if they were happening today. And the deeper you look into the night sky, the further back those layers of time reach, stretching past centuries, past whole millennia, all the way to galaxies so distant that their ancient light carries news from a universe almost too young to recognize. On a clear, dark night, far from city lights, you can spot a faint smudge in the sky using nothing but your own eyes, and that smudge is the most distant object visible to the naked human eye. That smudge is the Andromeda Galaxy, home to roughly 1 trillion stars, sitting about 2.5 million light-years away from Earth. The light entering your eyes right now, if you manage to spot it, left Andromeda 2.5 million years ago, long before modern humans existed, back when early human ancestors were only just beginning to walk upright across the plains of Africa. 2.5 million years is a staggering amount of time by any human measure. Civilizations rise and fall in a few thousand years. Written history stretches back roughly 5,000 years. 2.5 million years dwarfs all of that combined, over and over again, 500 times over. Yet that entire staggering stretch of time means nothing at all to the light itself. Exactly 0 seconds passed for those photons, according to their own frozen internal clock, during the entire 2.5 million year crossing. Picture an Olympic runner completing a marathon so fast that, according to their own body, no time passed between the starting gun and the finish line, even though the crowd watching from the sidelines waited over 4 hours for them to finish. That gap between the runner's experience and the crowd's experience captures, in a small way, the impossible gap between how light experiences its journey and how we experience watching it arrive. Andromeda is not just an object floating quietly in the distance, it is on a slow collision course with our own Milky Way galaxy, expected to merge with us in roughly 4 billion years, an event so far in the future that Earth's sun will likely have changed dramatically by the time it happens. The light leaving Andromeda tonight is a snapshot of it as it existed long before that collision even became a certainty, a picture from deep in the galaxy's past, arriving patiently across unimaginable distance. Here is a wrinkle worth pausing on. Everything you can see in the Andromeda Galaxy tonight already changed, updated, and moved on 2.5 million years ago. Individual stars inside it have already been born and died in the time since that light left. Entire star systems have shifted position. Yet the picture arriving at your eyes tonight remains frozen exactly as it looked at the single moment those photons departed, completely unaware of everything that happened to their home galaxy after they left. This means the night sky is not really a live view of the universe at all. It is closer to a photo album, filled with snapshots taken at wildly different moments, some recent, some ancient beyond imagination, all displayed together as if they were happening in the same instant. Two stars sitting right next to each other in the sky might be showing you completely different points in history, one a recent photo and the other a message from thousands of years earlier, layered together without any warning label to tell them apart. Understanding that difference between distance and time, between a light year as a length and a light year as a delay, becomes the key to understanding everything else the universe has to show you. A common mistake trips up almost everyone the first time they hear the phrase light year, and clearing it up unlocks a much bigger picture of the universe. A light year sounds like it should measure time. Since the word year sits right there in the name, it does not. A light year measures distance, specifically the distance light travels in one full year, while moving at its constant, unchanging speed. 1 light year equals about 6 trillion miles. It is a unit of length, the same category as a mile or a foot, just built for measuring distances so enormous that ordinary miles become useless. Picture trying to measure the distance between two cities using inches. Technically possible, but the number would become so large and clumsy that nobody could use it practically. Astronomers face that exact same problem when measuring the universe. Distances between stars and galaxies are so enormous that miles alone produce numbers with dozens of digits, far too unwieldy for regular use. The light year solves that problem by using light's own fixed, reliable speed as a giant measuring stick. Here is where the confusion usually creeps in, because light years describe distances that took light an actual amount of time to cross. People often assume looking at something a certain number of light years away means looking directly at the passage of that same number of years. That part is actually true, and it is exactly why light years double as a strange kind of window into the past. But it is important to keep the two ideas separate. The light year itself is measuring distance. The delay you experience, watching ancient light finally arrive, is a separate consequence of that distance combined with light's fixed speed limit. Think of it like mailing a letter using a delivery service that always takes exactly 1 day per mile travelled. If a letter takes 10 days to arrive, you instantly know it travelled 10 miles. The delivery time becomes a stand-in for distance, without actually being the same thing as distance. Light years work in a nearly identical way, letting astronomers describe mind-bending distances using a number that quietly doubles as a delay in time. This double meaning becomes especially powerful once distances stretch into the millions or billions of light years. Saying a galaxy sits 1 billion light years away tells you two things simultaneously. First, exactly how far away that galaxy physically sits from Earth. Second, exactly how far back in time you're looking every single time you observe it, since its light has spent 1 billion years crossing the gap to reach you. Grasping this distinction changes how you look at the entire night sky. Every star, every galaxy, every faint smudge of light carries both a distance and a delay bundled together into a single number. The farther away something sits, the further back in time its light was born. Stretching backward through history, the deeper astronomers look into space, all the way toward galaxies so distant that their light was already ancient before Earth itself had finished forming. A single number, printed under a photo in a textbook, can quietly hold both a length longer than anything on Earth and a delay longer than human civilization itself, hiding an entire story inside 3 ordinary-looking words. Astronomers pointed a telescope at what looked like an empty patch of black, featureless sky, and waited. That telescope, one of the most powerful ever built, stared at that single tiny patch of darkness for hours, collecting every faint scrap of light drifting in from the depths of space. What emerged from that patient wait stunned scientists around the world. The supposedly empty patch of sky was not empty at all. It was packed edge to edge with thousands of galaxies, each one holding billions of stars of its own, hiding in plain sight, too faint and too distant for ordinary observation to ever reveal. Among those thousands of faint smudges, astronomers found something record-breaking. A single galaxy whose light had travelled for over 13 billion years before finally reaching that telescope. 13 billion years is almost impossible to picture using anything from daily life. The universe itself is only about 13.8 billion years old. That means the light captured in that photograph left its galaxy when the universe itself was still practically a newborn, barely 5% of its current age. Picture flipping through a family photo album containing a single picture taken almost immediately after your great-great-great-grandparent was born, generations upon generations before you existed, and somehow having that photograph delivered straight to your door today, undamaged, unedited, exactly as it looked the moment it was taken. That is roughly the scale of what astronomers are holding when they study light from a galaxy this ancient and this far away. This galaxy did not just happen to be extremely distant. Its light needed the entire history of the universe, minus a small sliver at the very beginning, just to complete the crossing to Earth. To find something farther away, astronomers would essentially need to look before the universe itself finished forming its first stars, a boundary that no telescope has ever managed to cross. Every single photon captured in that image spent over 13 billion years travelling non-stop through the emptiness of space, and yet, according to that light's own internal clock, exactly 0 seconds passed during the entire staggering journey. Here is the part that stretches the imagination even further. That ancient galaxy almost certainly does not even look the way it appears in the photograph anymore. 13 billion years is enough time for entire generations of stars to be born, live out their lives, and die completely, replaced by newer generations in turn. The galaxy captured in that image might have grown, merged with neighbouring galaxies, or changed its shape entirely by now. Nobody on Earth will ever know its true current appearance, since any updated light describing those changes would also need over 13 billion years just to arrive. Every time astronomers push their telescopes to detect fainter, more distant light, they are pushing backward through time itself, edging closer and closer to the very beginning of the universe. Each new record broken, each fainter smudge finally captured, moves the frontier of human knowledge a little closer to the first flicker of light the universe ever produced. And there exists one particular kind of light, older than every galaxy, every star and every named object in the sky combined, marking the absolute oldest boundary that any telescope on Earth will ever be able to see. Point a sensitive enough antenna at literally any direction in the sky, and it picks up a faint, steady hiss, the exact same static in every direction without fail. That static is not radio interference from Earth, and it is not noise from faulty equipment. It is light, the oldest light that any instrument will ever detect, arriving from every single direction in the universe simultaneously. Scientists call it the cosmic microwave background, and it is essentially a fossil, a frozen leftover snapshot from when the entire universe was still a newborn baby, barely 380,000 years old. Here is the story behind it. In the earliest moments after the universe began, everything was packed together so tightly and so hot that light could not travel freely at all. Space itself was filled with a dense, glowing fog of particles, constantly scattering any light that tried to move through it, similar to how thick fog scatters a car's headlights, turning a sharp beam into a diffuse, useless glow. Light simply could not escape that fog and travel in a straight line. Before that moment, the universe would have looked completely dark and impenetrable to any observer, no matter how sensitive their equipment. Then, roughly 380,000 years after the beginning, the universe finally cooled down enough for that fog to clear. Particles combined into atoms, space became transparent, and light was finally free to travel in straight lines for the very first time in the universe's short history. That very first burst of freed light is exactly what scientists detect today as the cosmic microwave background, still travelling outward, still arriving on Earth, completely unchanged in its journey since the moment it was released. Picture a marching band trapped inside a thick, muffled fog bank, their music completely garbled and directionless. The instant that fog finally lifts, their music suddenly rings out clear and sharp in every direction at once. That first clear note is similar to what happened when the universe's fog cleared, releasing light in every direction simultaneously, a burst that has been travelling outward, uninterrupted, for over 13 billion years since. This ancient light has stretched dramatically during its impossibly long journey, transformed by the expansion of the universe itself from a brilliant hot glow into faint, cold microwave static. The same static that early radio and television antennas accidentally picked up decades ago, completely unaware they were detecting the oldest light in existence. Scientists eventually realized that a small fraction of the random static crackling on an old analog television screen was, in tiny part, the afterglow of the universe's own birth, arriving quietly into people's living rooms without anyone realizing it. Every direction you point an antenna, this same ancient light arrives, evenly spread across the entire sky, a nearly perfect fingerprint left behind from the universe's very first moments of existence. Nothing else detectable by human instruments reaches back further in time. Two scientists who first detected this signal by accident, while trying to fix what they assumed was a broken antenna, ended up winning a Nobel Prize for stumbling onto the oldest light in existence. This static marks the true edge of observable history, the oldest message the universe has ever sent, and it raises one final natural question about exactly how old the glow reaching your antenna truly is. Every telescope on Earth eventually runs into the exact same invisible wall, no matter how powerful it becomes or how far into space it manages to peer. That wall is the cosmic microwave background, and it marks the absolute oldest light that human eyes, or any instrument built by humans, will ever be capable of detecting. Beyond this glow lies the earlier fog described before, the dense, opaque haze filling the newborn universe, a period when light could not travel freely at all. No telescope, no matter how advanced, can ever see directly through that fog, because no light escaped it to carry a picture forward through time. This means the oldest light reaching Earth today left its source about 380,000 years after the universe began, and it has been travelling ever since, across the entire remaining stretch of the universe's 13.8 billion year history. That gap between the universe's absolute beginning and this ancient light's departure will likely remain permanently invisible, forever hidden behind a curtain no telescope can pull back. Picture trying to see through a frosted glass shower door. No matter how bright a light shines on the other side, the frosted glass scatters everything into a useless blur, hiding any clear picture completely. The dense early universe worked exactly the same way, permanently scattering and blurring any light trying to escape, until the fog finally cleared and light broke free for the first time. Everything before that moment stays hidden behind the equivalent of a cosmic frosted glass door blocked from view forever. Scientists have built entire careers studying tiny, subtle variations in this ancient glow, patches barely warmer or cooler than their surroundings by a fraction of a degree. Those faint variations, though almost imperceptibly small, mark the earliest seeds of structure in the universe, the tiny irregularities that eventually grew into galaxies, galaxy clusters, and everything else populating the night sky today. In a very real sense, every star, every planet, and every person alive today traces their earliest cosmic origin back to patterns frozen into this ancient light. This oldest possible light did not just happen to survive its incredible journey by luck. It survived because nothing in the entire universe can outrun it or catch up to erase it. Once released, it kept travelling in every direction at the same fixed speed. Light has always moved at, stretching and cooling along the way, but never disappearing, never fading into nothing, always present, always detectable by anyone with the right instrument pointed at the right patch of sky. Human eyes will never see anything older than this glow, no matter how technology advances in the centuries ahead. It stands as an absolute boundary, a wall built into the very structure of the observable universe itself. Everything humanity has ever learned about the cosmos, every star charted, every galaxy photographed, every distant light source ever studied, exists somewhere between this ancient boundary and the night sky glittering right outside your window tonight. That entire span, from the oldest visible glow to the closest twinkling star, represents the complete library of everything light has ever managed to deliver to human eyes. Light does not always travel in straight, simple lines through empty space forever, though. Sometimes it runs directly into something powerful enough to bend its path entirely. A star drifts too close to something invisible, and without warning, its light begins bending in ways that break every rule you thought space obeyed. That invisible object is a black hole, a region where gravity has become so overwhelmingly powerful that nothing, not even light, can escape once it crosses a certain boundary. Black holes form when massive stars collapse in on themselves at the end of their lives, crushing an enormous amount of material into an incredibly small space. The result is gravity so intense that it warps the space around it, bending the paths of anything passing nearby, including beams of light that happen to wander too close. Here is the part that seems impossible at first. Light has no mass, and gravity, in the simplest everyday explanation, pulls on mass. So how could gravity possibly bend something that has no mass to grab onto at all? The answer flips the entire question around. Gravity bends space itself, warping the very fabric that light has to travel through, rather than pulling directly on the light. Light always travels in the straightest possible path available to it. Near a black hole, the straightest available path simply is not straight anymore, because space itself has been curved. Picture a bowling ball resting on a stretched trampoline, creating a deep dip in the fabric. Roll a marble anywhere near that dip, and its path curves toward the bowling ball, not because the marble is being pulled directly, but because the surface it travels across has been bent. Light passing near a black hole behaves in a remarkably similar way, curving along a warped path through space itself, without ever being pulled or grabbed directly. Now bring back the idea of light's own frozen personal clock, and something even stranger emerges. As light approaches a black hole, gravity bends its path and also affects time itself, in a phenomenon called gravitational time dilation. The stronger the gravity, the slower time passes for anything nearby, including light. From an outside observer's point of view, light nearing a black hole appears to slow down dramatically, stretching out and dimming as it approaches the boundary of no return, called the event horizon. But remember, light's own personal clock was already frozen at 0 seconds, long before it ever encountered a black hole. Gravity cannot make an already frozen clock freeze any further. Instead, gravitational time dilation changes how outside observers perceive that light, stretching its wavelength and slowing its apparent motion, without ever touching the light's true, unchanging internal experience of 0 elapsed time. Astronomers have photographed the eerie, glowing ring of light bent around real black holes, capturing images that once existed only in theoretical equations. That glowing ring is made of light desperately circling the edge of the point of no return, some of it captured forever, some of it slingshotting back out into the universe, forever marked by the extreme gravity it barely escaped. Even in the most extreme environment the universe has to offer, light's ancient rule holds firm, its clock permanently frozen at 0 no matter how violently the space around it gets twisted and bent. Some light bends near a black hole and continues safely on its way. Other light gets trapped forever, circling endlessly in a place with a name as strange as the phenomenon itself. Point a powerful telescope at the center of a black hole's shadow, and something strange comes into view. A thin, glowing ring where light itself gets trapped in an endless looping orbit. That ring marks the photon sphere, a razor-thin boundary surrounding a black hole where gravity bends space so severely that light can no longer travel in a straight line at all. Instead, light entering this zone at just the right angle gets bent into a perfect circle, orbiting the black hole over and over, trapped in a loop with no beginning and no end. This is not the same as falling past the point of no return, called the event horizon, where light and everything else gets pulled in permanently, never to escape again. The photon sphere sits just outside that final boundary, a strange middle ground where light is not quite captured forever, yet cannot break free in a straight line either. Light circling at exactly the photon sphere's distance keeps circling indefinitely, caught in a delicate, unstable balance between escaping outward and falling inward. Picture a marble rolling around the very rim of a bowl, spinning endlessly along the highest edge without falling all the way to the bottom and without rolling back out over the top. That balance is delicate and easily broken. The slightest nudge sends the marble tumbling one way or the other. Light at the photon sphere behaves the same way. The tiniest disturbance, the faintest gravitational ripple passing through, can send that orbiting light either spiralling inward toward permanent capture or spiralling back outward into the wider universe. Remember that light's own personal clock has been frozen at 0 seconds since the very beginning of this journey. Circling a black hole forever changes absolutely nothing about that fact. A photon trapped in an endless loop around the photon sphere still experiences exactly 0 time passing, no matter how many trillions of times it circles. From an outside observer's point of view, watching light spin around a black hole for what looks like an eternity, the light itself experiences that eternity as nothing at all, a single frozen instant stretched into infinite repetition. Astronomers used exactly this glowing ring to capture the very first photograph of a black hole ever taken, released to the public in 2019. That famous, blurry orange ring surrounding a dark centre was not the black hole itself, since a black hole by definition emits no light of its own. The glowing ring was light from the photon sphere, bent and captured mid-orbit, showing scientists around the world direct visual proof of a phenomenon that had existed only in equations for over a century. Researchers combined signals from telescopes scattered across the entire planet, effectively building a single instrument as large as Earth itself, just to capture that one faint, glowing image. This trapped light offers a strange kind of monument, proof that gravity can twist the path of something with no mass strongly enough to build an invisible prison made entirely out of curved space. Nothing physical holds that light in place. No wall, no barrier, nothing solid at all. Only the shape of space itself, bent by gravity into a loop so tight that light has nowhere else to go. And this bending of light is only the surface of a much bigger story. Gravity reaches deeper still, slowing down the flow of time itself for anything caught nearby. A distortion that grows more extreme the closer you creep toward the black hole's final, inescapable edge. A clock sitting at the bottom of a tall mountain ticks slightly slower than an identical clock placed at the mountain's peak, and the difference has nothing to do with altitude sickness or thin air. This is gravitational time dilation, a companion effect to the speed-based time dilation covered earlier, except this version comes from mass alone rather than motion. The stronger the gravity pulling on a location, the slower time passes there compared to a location with weaker gravity. Down near sea level, Earth's gravity pulls slightly stronger than it does high up a mountain, farther from the planet's centre. That tiny difference in gravitational strength creates a tiny, measurable difference in how fast time flows. A person living their entire life at sea level would, in principle, age very slightly less than an identical twin who spent that same lifetime living at the top of a tall mountain, purely because of this gentle gravitational stretch. Scientists have actually measured this effect using clocks separated by mere inches in height, using instruments precise enough to detect differences of a few parts in a quadrillion. A clock sitting on a lower shelf genuinely ticks slower than an identical clock sitting on a shelf just above it, purely because it sits fractionally closer to the centre of Earth's gravity. This tiny effect adds up dramatically once gravity grows far stronger than anything found on Earth's surface. Near an object as massive and dense as a black hole, gravity grows so extreme that time dilation becomes impossible to ignore. Picture a clock lowered slowly toward a black hole on a very long cable. As it descends closer and closer to the event horizon, an observer watching from a safe distance would see that clock ticking slower and slower, stretching each second into what looks like minutes, then hours, then years. Right at the event horizon itself, the outside observer would see the clock's hands appear to freeze completely, seemingly never quite reaching that final boundary at all, even though time keeps passing normally from the descending clock's own point of view. Here is a helpful comparison. Imagine pouring honey from a jar. Near the top, where the honey has not built up speed yet, it flows quickly and freely. Farther down, where the honey slows and thickens against the sides of the jar, its flow drags and stretches out. Gravity acts on time in a similar way, thickening and stretching it out the closer you get to an enormous mass, until near a black hole's boundary, time barely flows at all from an outside point of view. This means mass alone, without any motion whatsoever, can stretch time dramatically, echoing everything discovered earlier about speed stretching time in a completely different way. Both effects, motion and mass, bend time according to the exact same underlying theory, simply approaching the distortion from two different directions. A spacecraft travelling near light speed, and a spacecraft parked motionless, but sitting deep inside intense gravity, would both experience time passing slower than someone floating freely in empty space far away. Light itself sits at the strange meeting point of both effects, always moving at the maximum possible speed, while constantly threading through regions of varying gravity throughout the universe, its wavelength stretching and its path bending, depending on exactly what massive objects it happens to pass along the way. And there exists an entirely different way for light to stretch across vast distances, one that has nothing to do with black holes at all, caused instead by the expansion of the universe itself. Stretch a rubber band with dots drawn along its length, and every dot drifts farther apart from every other dot, without any single dot actually moving on its own. That simple stretching rubber band captures something enormous happening across the entire universe right now. Space itself is expanding, growing larger every single moment, carrying galaxies farther apart from each other. The space between them keeps stretching wider and wider, like the rubber band pulling those dots apart, rather than the galaxies themselves flying through space under their own power. Astronomers first discovered this expansion nearly a century ago, watching distant galaxies drift apart from each other in every direction, a discovery that completely reshaped how scientists picture the size and history of the universe. Light travelling across this stretching space gets stretched right along with it, a phenomenon called cosmological redshift. As a beam of light crosses billions of miles of expanding space on its way to Earth, the wavelength of that light literally stretches longer during the journey, shifting its colour toward the red end of the visible spectrum. The farther light has travelled, and the more space has expanded during that journey, the more dramatically its wavelength stretches by the time it finally arrives. Picture an ambulance driving away from you with its siren blaring. As the ambulance pulls farther away, the pitch of its siren drops lower and lower, stretched out by the increasing distance. Light behaves in a related way when the space it travels through keeps expanding, its colour stretching toward red the same way that siren's pitch stretches toward a lower note. Astronomers use this exact stretching, measured with extreme precision, to calculate how far away a distant galaxy sits and how fast the space around it is expanding. The greater the redshift measured in a galaxy's light, the faster that galaxy is being carried away, and the farther back in cosmic history its light must have originally departed. This stretching effect grows so extreme for the most distant galaxies that visible light gets stretched entirely out of the range human eyes can detect, shifted instead into infrared or even radio wavelengths by the time it reaches Earth. Telescopes built to hunt for the earliest galaxies in the universe have to search specifically for this stretched reddened light, since the ordinary visible light those galaxies originally emitted has been stretched completely beyond what any human eye could ever perceive. Here is where things connect back to everything already covered. A photon leaving a distant galaxy still experiences exactly 0 seconds of its own personal time during the entire journey, no matter how dramatically its wavelength gets stretched along the way. The stretching happens to the light's colour and energy, a change caused by the space it travels through, expanding underneath it. It does not happen to the photon's own frozen internal clock, which remains locked at 0 regardless of how much cosmic redshift its wavelength has picked up, by the time it lands on a telescope's detector. This constant stretching, happening across the entire universe simultaneously, leads to a discovery that unsettled scientists the moment they fully understood its consequences. Space expands gently and evenly across most regions, but across truly enormous distances, that expansion adds up and grows fast enough to outrun light itself, creating a boundary that some starlight will never manage to cross. Somewhere out in the depths of space, a galaxy is moving away from Earth faster than light itself can travel, and this breaks no laws of physics whatsoever. That statement sounds impossible at first, since nothing with mass can ever reach or exceed light speed, a rule covered earlier in this very story. The trick lies in exactly what is doing the moving. That distant galaxy is not racing through space under its own power at some impossible velocity. The space between Earth and that galaxy is expanding so rapidly that the total distance between the two grows faster than light could ever cross it, even though neither Earth nor that galaxy is physically moving through space at anything close to light speed. Picture two ants standing on opposite ends of a giant balloon as someone inflates it rapidly. Neither ant is walking anywhere. Both stay perfectly still on the balloon's surface, yet the distance separating them grows larger and larger as the balloon expands beneath their feet, potentially growing faster than either ant could ever walk to close that gap. Galaxies separated by the ever-expanding universe face a nearly identical situation, standing still relative to their own local space, while the space itself inflates the total distance between them. The farther apart two galaxies sit to begin with, the faster that gap grows, since there is simply more expanding space stacked up between them. This creates a genuinely strange and permanent consequence. Light leaving a sufficiently distant galaxy today may never actually reach Earth, no matter how much time passes in the future. If the space between that galaxy and Earth keeps expanding fast enough, the light chasing toward us gets outpaced by the growing distance itself, like a swimmer trying to cross a river that keeps widening faster than they can swim. That light remains forever trapped on the far side of an invisible boundary, permanently unable to complete its journey. Astronomers call this boundary the cosmic horizon, the farthest distance from which light will ever be capable of reaching Earth, now or at any point in the future. Beyond that horizon lies an enormous portion of the universe Earth will simply never be able to observe, no matter how advanced telescopes eventually become. Building a stronger telescope will never solve this problem. Some regions of the universe are permanently cut off from view, hidden behind an edge that keeps retreating faster than any signal could chase it down. Here is the strangest part of all. This cosmic horizon is not fixed in place. As the universe continues expanding, more and more galaxies are gradually crossing beyond that boundary, their light slowly fading and finally winking out of reach forever. Billions of years from now, an observer on Earth, or whatever exists here by then, would look up at a night sky containing dramatically fewer visible galaxies than exist today, since most of them will have drifted beyond the reach of light entirely. This means the universe is quietly, continuously erasing itself from view, one galaxy at a time, an inevitable and unstoppable expansion carrying entire islands of stars beyond any hope of ever being witnessed again. Nothing about this slow fade can be stopped, reversed, or outrun, since it comes from the very shape and growth of space itself rather than any single object moving through it. And this same expanding boundary raises an unsettling question about galaxies humanity can currently see, wondering exactly how many of them might already be crossing that invisible edge right now, without anyone on Earth realizing it. A galaxy visible through a telescope tonight might already be gone from view forever by the time your grandchildren look through that same telescope. This happens because of the expanding cosmic horizon covered just before, the invisible boundary marking the farthest distance light will ever be able to travel to reach Earth. Galaxies sitting near the very edge of that boundary today are slowly, steadily crossing beyond it as the universe keeps expanding, their light gradually fading and stretching, until it eventually disappears from view completely, never to be recovered by any telescope, no matter how powerful. Picture watching a ship sail toward the horizon out at sea. At first, the entire ship stays clearly visible. Slowly the hull dips below the horizon line first, followed eventually by the mast, until finally nothing remains visible at all, even though the ship itself continues sailing along just fine on the other side. Distant galaxies crossing the cosmic horizon disappear from Earth's view in a strangely similar way, their light stretching and dimming gradually rather than vanishing all at once in a single dramatic instant. No sudden flash marks the moment, no final signal announces the departure, only a slow, quiet fade spread across an enormous stretch of time. Here is a detail that makes this process even stranger. From Earth's perspective, a galaxy approaching the cosmic horizon never appears to fully vanish in a clean, sudden moment. Instead, due to the way light stretches as it fights against ever-expanding space, that galaxy's light grows fainter, and more stretched out gradually, approaching the boundary in slow motion that could theoretically stretch across an incredibly long span of time, technically approaching but never quite completing the disappearance, similar to how time near a black hole's event horizon appeared to freeze from an outside observer's perspective. This creates an odd kind of cosmic illusion. A galaxy might be considered, by strict definition, already beyond the point where any new light could ever reach Earth, yet older light from that galaxy, light that departed before it crossed that boundary, could still be slowly, faintly arriving, fading a little more with each passing year, a ghost image lingering long after the source itself became permanently unreachable. Scientists studying the most distant visible galaxies today are essentially racing against this slow fade, gathering as much information as possible about regions of the universe that are gradually slipping beyond the reach of observation. Every year that passes, a small number of galaxies drift closer to that permanent boundary, shrinking the total portion of the universe that will ever be available for study, explored, or understood by anyone on Earth now or at any point far into the future. Future scientists born long after everyone alive today will inherit a smaller, quieter slice of the observable universe than the one visible tonight. Think about everything covered so far. Light itself never ages during its journey, yet the space it travels through keeps stretching, sometimes so aggressively that light can never complete certain journeys at all. Time bends near massive objects and stretches with speed. Entire galaxies vanish permanently beyond boundaries humanity cannot cross. Light seems, at every turn, defined mostly by limits, boundaries it cannot exceed, and races it cannot win against the universe's own expansion. Yet despite carrying no mass, and facing constant limits on where it can travel, light carries something else entirely, an invisible kind of force capable of physically pushing objects across the emptiness of space. Point a bright flashlight at your open palm and you will feel absolutely nothing, yet that beam of light is physically pushing against your skin at every single moment it shines, a force too gentle to feel but too real to deny. This tiny, imperceptible push is called radiation pressure, a real physical force created by light striking any surface, despite the fact that light carries zero mass. The force involved is astonishingly small, far too weak for human skin to ever detect directly. A powerful spotlight shining directly on your hand for an entire lifetime would still apply less pressure than a single falling snowflake landing gently on your skin. Yet this force is completely real, measured and confirmed repeatedly using extremely sensitive laboratory instruments, tucked away inside sealed chambers designed specifically to filter out every other competing force in the room. Here is how something with no mass at all manages to push on physical objects. Light carries energy and momentum, even without carrying mass. A strange fact built directly into the physics of how light behaves. When light strikes a surface, it transfers a tiny fraction of that momentum into the object it hits, creating a gentle, continuous push in the direction the light is travelling. It works somewhat like tiny, weightless raindrops constantly striking an umbrella, each drop contributing an infinitesimally small nudge that, multiplied across countless drops, becomes a force you can genuinely feel. Multiply that same idea by the trillions of photons striking a surface every second, and an effect too small to notice individually becomes measurable as a whole. This effect stays completely unnoticeable in ordinary daily life, buried far beneath the pull of gravity, the resistance of air, and the countless other forces constantly acting on objects here on Earth. Step outside the protective blanket of Earth's atmosphere and gravity, though, into the emptiness of space, and radiation pressure suddenly becomes a force capable of doing real, measurable work over time, even though any single moment of that push remains almost impossibly gentle. In that emptiness, with no air resistance and almost no competing forces left to overpower it, even the gentlest push finally gets the chance to matter. Picture pushing a shopping cart across an enormous, perfectly frictionless parking lot using nothing but your gentlest possible breath. A single breath alone would barely nudge the cart forward at all. Keep breathing on it steadily for hours though, with absolutely nothing slowing the cart down along the way, and that consistent, gentle push would eventually build the cart up to a genuinely impressive speed. Radiation pressure in space behaves in a nearly identical way. applying a constant gentle push that, given enough uninterrupted time, can accelerate an object to remarkable speeds. Scientists first predicted this strange pushing force mathematically, long before technology existed capable of measuring it directly in a laboratory setting. Decades of careful experiments eventually confirmed the prediction precisely, measuring the tiny but completely real pressure exerted by light-striking mirrors and detectors under carefully controlled conditions. Engineers, watching those careful confirmations pile up over the decades, began imagining a completely different kind of spacecraft built entirely around this gentle, invisible push. This confirmed force, though gentle beyond ordinary human perception, opened the door to an entirely new kind of spacecraft, one that needs no fuel, no engine, and no combustion whatsoever, powered instead purely by sunlight pressing continuously against an enormous reflective sail unfurled across the emptiness of space. A spacecraft the size of a tennis court unfurls a massive mirror-bright sail in the emptiness of space, and begins accelerating using nothing but sunlight itself. This is a solar sail, a real spacecraft technology already tested successfully in orbit, powered entirely by the gentle push of radiation pressure covered just before. Instead of burning fuel like a traditional rocket, a solar sail simply spreads an enormous ultra-thin reflective sheet, sometimes thinner than a human hair, and lets sunlight bounce off its surface continuously, gaining a tiny push with every single photon that strikes and reflects away from it. A single photon striking that sail contributes an amount of push so small it defies easy comparison, but sunlight delivers an absolutely staggering number of photons every single second, constantly, without ever running out or needing to be refueled. Multiply that tiny push by the sheer, relentless quantity of photons striking a large enough sail, hour after hour, day after day, and the spacecraft gradually builds up genuinely impressive speed, all without carrying a single drop of fuel on board. Traditional rockets run out of thrust the moment their tanks empty, while a solar sail simply keeps gaining speed as long as sunlight keeps arriving. Picture a sailboat catching wind across open water, gradually building speed as the steady breeze keeps pushing against its sail, hour after hour, without the boat needing an engine at all. A solar sail works using the exact same basic principle, except instead of catching wind, it catches light, using sunlight's own gentle radiation pressure as an endless, self-replenishing source of propulsion that never runs low, so long as the spacecraft keeps facing toward a star. This gives solar sails one enormous advantage over traditional rockets. Chemical rockets carry all their fuel from launch, and once that fuel runs out, acceleration stops completely. A solar sail, by contrast, keeps gently accelerating for as long as it remains within range of sunlight, strong enough to push against its surface, gradually building toward remarkable speeds over the course of months or years, entirely without needing to carry, store, or burn any fuel whatsoever. The trade-off comes in patience, since a solar sail accelerates far more gently than a rocket engine, trading a fast, violent launch for a slow, steady climb that eventually pays off. Engineers have already tested working solar sails in real space missions, successfully proving that spacecraft can be steered and accelerated purely through carefully angled sunlight pressure. Some scientists have proposed even more ambitious versions of this idea, using enormous, powerful lasers fired from Earth, instead of relying only on natural sunlight, potentially pushing a small, lightweight probe to a meaningful fraction of light speed, fast enough to reach a nearby star system within a single human lifetime, rather than tens of thousands of years using traditional propulsion. This entire technology exists because light, despite having zero mass, still carries real, usable force capable of steadily accelerating a physical spacecraft across the emptiness of space. It stands as living proof that everything strange and abstract about light discussed so far, its fixed speed, its frozen internal clock, its total lack of mass, translates directly into genuine practical engineering happening today. And light's strangeness does not stop with gentle invisible pushes through empty space. Under exactly the right conditions, light can even appear to be broken, outrun by particles racing through a medium that slows light down far below its usual blistering pace. Deep inside a nuclear reactor's cooling pool, an eerie, glowing blue light shines continuously, and its cause seems, at first glance, to break one of the most fundamental rules covered throughout this entire story. That glow is called Cherenkov radiation, and it appears whenever a charged particle moves through water or another transparent material faster than light itself can travel through that exact same material. This sounds impossible at first, since nothing can ever outrun light. The resolution lies in a small but crucial detail. Light's true, absolute speed limit, 186,000 miles per second, only applies to light travelling through the emptiness of a complete vacuum. Light actually slows down noticeably when passing through denser materials like water, glass, or air, sometimes losing as much as 25% of its top speed while pushing through something as ordinary as water. A fast-moving charged particle, released during certain nuclear reactions, can absolutely travel faster than that slowed-down version of light, while still remaining safely below light's true, unbreakable speed limit measured in a vacuum. When this happens, the particle creates a phenomenon similar to a sonic boom, except built from light instead of sound. Just as a jet breaking the sound barrier creates a shockwave of compressed air trailing behind it, a particle breaking the local speed of light in water creates a shockwave of light itself, releasing that distinctive, eerie blue glow along its path. No rule of physics gets broken in the process, since the particle never comes close to matching light's true top speed measured through empty space. Picture a speedboat racing across a lake faster than the ripples it creates can spread outward. Those ripples pile up behind the boat, forming a distinctive wake trailing in its path. Cherenkov radiation forms in a nearly identical way, except the ripples are made of light instead of water, piling up behind a particle outrunning light's locally reduced speed limit inside that particular material. This striking blue glow serves a genuinely practical purpose beyond simply looking dramatic. Scientists studying nuclear reactors use the intensity and pattern of Cherenkov radiation to monitor exactly how much radioactive activity is happening inside a reactor's core at any given moment, without needing to insert sensitive instruments directly into the intensely radioactive water itself. Physicists studying particles from deep space, including ghostly particles called neutrinos, also rely on detecting this exact same blue glow, using massive underground tanks of pure water surrounded by extremely sensitive light detectors, waiting patiently to catch the faint flash whenever a rare, high-energy particle happens to pass directly through. Some of these detectors sit buried thousands of feet underground, shielded from ordinary interference, quietly listening for a flash of light that might arrive only a handful of times each year. Cherenkov radiation does not in any way break light's true speed limit measured through empty space. It simply reveals what happens when something moves faster than a locally reduced version of that limit, exposing a genuine physical shockwave built entirely from light itself. This strange glowing exception actually reinforces the very same rule it initially appears to break, proving once again just how absolute and unbreakable the true, vacuum-based speed of light truly is. Yet even that absolute speed limit runs into one final, deeply strange exception, a phenomenon involving particles that seem to communicate instantly across enormous distances, without technically sending any information faster than light at all. Separate two particles by the entire width of a galaxy, measure one of them, and the other particle instantly reflects that exact measurement. No delay, no waiting, no travel time whatsoever. This bizarre phenomenon is called quantum entanglement, and it involves pairs of particles linked together in a strange deep way at the moment of their creation. Once entangled, measuring a property of one particle, something like its spin or polarization, instantly determines the corresponding property of its partner particle. Even if that partner sits an enormous distance away, separated by more space than light itself, could cross in a reasonable amount of time. Einstein himself found this deeply troubling, famously describing it as spooky action at a distance, a phrase that has stuck around in physics ever since. Here is why this does not actually break light's speed limit, despite appearing to at first glance. The measurement itself does not send any usable information from one particle to the other. Before either particle gets measured, the outcome of that measurement remains genuinely random and completely unknown, even to the particles themselves. Only after both measurements happen, and scientists compare notes using an ordinary conventional method that itself cannot travel faster than light, does the strange correlation between the two results actually become apparent and useful. Picture two sealed envelopes, prepared together, each containing a card that says either heads or tails, guaranteed to always match each other perfectly, though nobody knows which one until an envelope gets opened. Mail one envelope to a friend on the opposite side of the planet. The instant you open your envelope and see heads, you technically know your friend's envelope also says heads, without needing to contact them at all. But you still cannot use this trick to actually send your friend a message faster than the mail truck carrying their envelope could travel, since the outcome itself was random and fixed the moment the envelopes were originally prepared. Quantum entanglement behaves in a conceptually similar way, though far stranger under the hood, since physicists have proven, through decades of increasingly clever experiments, that the particles are not simply carrying hidden, predetermined answers the entire time, the way the envelopes secretly do. Something genuinely stranger is happening, a correlation that exists instantly across any distance, without any signal, particle, or piece of information actually crossing the gap between them at light speed or faster. Even Einstein, one of the sharpest minds ever to study the universe, spent years trying and failing to explain the effect away using ordinary, everyday logic. Scientists have tested entanglement across distances spanning hundreds of miles, using satellites in orbit to send entangled particles down to separate ground stations on opposite sides of a country, confirming the correlation holds up perfectly even across enormous real-world distances. This confirms, again and again, that light's speed limit remains completely intact and unbroken, since no actual information, message, or usable signal ever travels between the entangled particles faster than light could carry it through ordinary means. This strange exception, one that looks like it breaks the rules while actually reinforcing them, points towards something even deeper, running underneath the entire universe, a reason why light speed seems to sit at the very center of nearly every physical law discovered so far, acting less like an arbitrary number and more like a fundamental boundary woven directly into the fabric of reality itself. Every single measurement of light speed, taken across more than a century of increasingly precise experiments, has landed on the exact same number, 186,000 miles per second, without a single confirmed exception ever found anywhere in the universe. This alone would be remarkable enough, but light speed turns out to be woven into far more than just how fast light itself travels. It shows up repeatedly throughout the deepest equations describing energy, mass, gravity, and the structure of space and time itself. Einstein's most famous equation links energy directly to mass using light speed as the connecting number, squared. That single number, first measured using mirrors and beams of light, turns out to govern how much energy sits locked inside every atom in the universe, whether that atom happens to be moving anywhere near light speed or not. Here is a strange way to think about it. Light speed is not simply a fact about light. It functions more like a universal speed limit built into the very fabric of reality, a limit that light happens to travel at because light has no mass to hold it back. Anything without mass, in theory, would also be forced to travel at that exact same speed for the same underlying reason. Light is not special because it created this speed limit. Light simply obeys a limit that already existed, built into the structure of space and time before light ever came along to demonstrate it. Gravitational waves, ripples in space itself with no mass of their own, travel at that exact same speed, offering further proof that the limit belongs to the universe rather than to light alone. Picture a racetrack with an absolute maximum speed permanently built into its pavement, a limit no car could ever exceed no matter how powerful its engine became. Cars with heavier frames struggle more to approach that limit, burning enormous amounts of fuel just to get close. A theoretical car with zero weight at all would face no such struggle, gliding immediately to the track's maximum speed the instant it started moving, since nothing would hold it back. Light behaves like that weightless car moving at the track's true maximum speed simply because nothing about light's own nature could ever slow it down. This deep connection explains why the same fixed number shows up again and again throughout completely different areas of physics, from how satellites calculate their position, to how nuclear reactors generate power, to how astronomers measure the size of the observable universe. It is not a coincidence that light's speed appears everywhere. It reflects the fact that space and time themselves are built around this one unbreakable limit, with light simply being the most visible, most familiar example of something actually reaching it. A messenger carrying proof of a rule far bigger than itself. Scientists have searched extensively for any hint that this speed limit might bend or break under extreme conditions, testing it near black holes, inside powerful particle accelerators, and across the vast stretches of the early universe. Every single test, without exception, confirms the same fixed number, reinforcing the idea that this is not simply a property of light, but a fundamental rule the entire universe quietly obeys. And once you accept that a beam of light is always racing along at this fixed, unbreakable limit, one particularly strange consequence returns to center stage, waiting to be pushed to its absolute most extreme conclusion. Ask a physicist what a beam of light experiences during its journey across the universe, and the honest answer sounds almost impossible to accept. It experiences nothing at all, not in the sense of blankness or emptiness, but in the sense that no experience unfolds across any span of time whatsoever. From light's own frozen point of view, its birth and its eventual absorption happen at exactly the same instant, with the entire journey in between compressed down to nothing. A photon leaving the sun and striking your skin 8 minutes later, a photon leaving a distant galaxy and striking a telescope's detector 14 billion years later, both experience their entire journey as a single, indivisible moment, with zero difference between them from the photon's own perspective. This idea stretches human imagination almost past its limit, because everything in daily human life unfolds gradually, moment by moment, across a clear, steady flow of time. A meal takes time to eat, a conversation takes time to unfold. Even the fastest events humans experience, a blink, a heartbeat, a flash of lightning, still involve some measurable stretch of time passing. Light offers no equivalent stretch whatsoever. Departure and arrival collapse into the exact same instant, with the entire distance in between simply erased from light's own point of view. No experience of a human life, however brief or intense, comes anywhere close to matching that absolute compression down to nothing. Picture folding a giant map in half, bringing two far apart cities together until they touch directly, with all the distance between them tucked invisibly into the fold. From light's own point of view, something similar happens to the entire universe. Every distance light ever crosses, whether across a room or across billions of light years, gets folded down to zero, with departure and arrival touching directly, no matter how vast the gap appeared to an outside observer, watching the whole journey unfold normally. The map itself never changes size. Only the fold determines how close 2 points end up sitting to each other. Physicists describe this using the earlier concept of proper time, the personal onboard clock belonging to anything travelling through the universe. For light, proper time simply never advances, staying locked at zero from the very first instant of creation until the final instant of absorption. This is not a rounding error too small to notice, buried somewhere deep in the math. It is the literal, complete answer, confirmed repeatedly through both theory and experiment, describing light's entire relationship with the passage of time, a relationship that never truly begins in any way a human mind naturally understands. This single fact recontextualizes everything covered throughout this entire journey. Every twinkling star overhead, every distant galaxy captured in a telescope, every beam of sunlight warming your skin, all of it represents light that has personally experienced 0 seconds passing, regardless of how many years, centuries, or billions of years ticked by according to clocks here on Earth. Light does not patiently wait out its journey the way a traveller counts down miles on a long road trip. It simply arrives, the instant it departs, according to its own internal experience, no matter how far away that departure point happened to be. Nothing in the physical universe travels lighter, faster, or stranger than something that experiences its entire existence in a single frozen breath. Stand outside on a clear night, and you're staring directly into the strangest gap in all of physics, a gap separating an entire eternity from absolutely nothing at all. For you, standing beneath that sky, real time is passing. Your heart beats. Your thoughts drift from one star to the next. Minutes tick by, marked by your own breathing, your own shifting weight from foot to foot as you crane your neck upward. Meanwhile, every single beam of starlight reaching your eyes at that exact moment has personally experienced 0 seconds of that same passage, regardless of whether it travelled 4 years from the nearest star system or 13 billion years from one of the earliest galaxies ever formed. You and that light occupy the exact same instant, yet arrived there by 2 completely different routes through time. This creates 2 completely different timelines occupying the exact same moment, layered directly on top of each other without ever touching. Your personal timeline stretches forward continuously, second by second, night after night, year after year, eventually spanning an entire human lifetime measured in decades. Light's personal timeline, by contrast, never stretches at all. It remains permanently frozen at 0, an eternity of distance and years compressed into an experience shorter than the shortest possible instant a human mind could ever imagine. Picture 2 rulers laid side by side, one stretching out for miles without end, marked with countless notches representing years, decades, centuries, even billions of years. The other ruler has no length whatsoever, a single point with no notches, no divisions, nothing to measure at all. Both rulers describe the exact same journey, the exact same beam of starlight crossing the exact same distance, yet one measures that journey as spanning an almost unimaginable eternity, while the other measures it as spanning literally nothing. No third ruler exists somewhere in between, offering a gentler, more moderate answer to soften the contrast. This gap is not a flaw or limitation in how scientists currently understand physics. It is a fully confirmed, mathematically precise consequence of light travelling at the absolute maximum speed the universe allows. The gap exists because speed and time are linked together in a way that has nothing to do with imagination or metaphor. As speed climbs toward light's maximum limit, the personal passage of time shrinks correspondingly, hitting exactly 0 the moment that limit gets reached, with no smaller number available beyond it. Every experiment ever designed to test this relationship has confirmed the same steady shrinking, right down to the theoretical 0 light alone reaches. Standing under that night sky, you occupy the human side of this gap, experiencing the full, patient stretch of years required for ancient starlight to finally arrive at your exact location. Every photon reaching your eyes occupies the opposite side entirely, having experienced none of that patient waiting whatsoever. 2 timelines, one stretching across billions of years, the other collapsed into nothing, meeting for a single fleeting instant, the moment that ancient light finally strikes your eye and disappears, ending a journey that, from its own point of view, never actually took any time to complete at all. That single meeting point, your patient years crossing paths with light's total absence of years, happens above your head every single night, whether you notice it or not. A photon leaves a distant star, crosses an unimaginable stretch of empty space, and finally strikes the back of a human eye, ending a journey that experienced exactly 0 seconds of its own passage. That single moment of absorption marks the true end of a photon's existence, a strange kind of death and birth happening simultaneously. The photon itself disappears entirely, converted instantly into a tiny burst of energy, absorbed by whatever it happened to strike. Whether that target is a human eye, a telescope's detector, a leaf performing photosynthesis, or a simple grain of sand warming slightly under direct sunlight. The photon does not slow down, does not linger, and does not fade away gradually. It simply ceases to exist as a photon, the instant it delivers its energy to whatever it struck, closing out a journey that, from its own frozen point of view, never technically began at all. Picture a runner completing a marathon by crossing the finish line and immediately dissolving into confetti, their entire journey converting instantly into a burst of celebration the moment they finish. That strange, instant transformation captures something close to what happens during a photon's absorption. There is no slowing down at the finish line, no gradual stop. There is only motion, followed immediately by complete transformation into something else entirely. Energy transferred completely and instantly into whatever waited at the end of the journey. No trailing off, no fading glow, only a clean, total handoff of energy in a single instant. This final moment carries enormous consequences depending on exactly what absorbs the photon. Inside a leaf, absorbed sunlight kicks off the chemical reactions of photosynthesis, eventually producing the oxygen filling Earth's atmosphere and the food supporting nearly all life on the planet. Inside a human eye, absorbed light triggers a chemical reaction inside specialized cells, sending an electrical signal racing toward the brain, ultimately becoming the sensation of sight itself. Inside a solar panel, absorbed sunlight knocks electrons loose, generating the electrical current powering homes, satellites, and spacecraft across the solar system. One tiny burst of energy, delivered the exact same way every time, ends up doing completely different jobs depending entirely on where it happens to land. Every single one of these outcomes, no matter how different they appear on the surface, traces back to the exact same underlying event, a photon completing a journey that, from its own point of view, took zero time to finish, then disappearing entirely the instant it delivered its energy to whatever waited at the finish line. The 8-minute journey from the Sun, the 4-year journey from Alpha Centauri, the 13 billion year journey from the most distant known galaxy, all end in this exact same way. A sudden, complete, and total transformation from light into something else entirely. This means every photon ever absorbed by anything, anywhere, throughout the entire history of the universe has followed the exact same strange rule. 0 seconds of personal experience, followed by complete disappearance, followed immediately by a transfer of energy into whatever waited on the receiving end. Multiply that single strange story by the uncountable trillions of photons striking Earth every single second, and an entirely new way of understanding sunlight, starlight, and vision itself begins to take shape, one built entirely around instants rather than durations, endings rather than gradual fades. Line up a human lifetime and a photon's lifetime side by side, and the comparison breaks apart almost immediately, refusing to fit onto any normal scale at all, no matter how carefully you try to force the two numbers into the same frame. A human lifetime unfolds gradually across roughly 80 years, filled with countless individual moments, each one distinct, each one following the last in a smooth, continuous flow. Childhood stretches into adolescence, which stretches into adulthood, which eventually gives way to old age, an entire rich sequence of experiences accumulated slowly across tens of thousands of days, each one containing its own smaller sequence of hours, minutes, and seconds. Birthdays mark the passage clearly, one candle at a time, building into a steady, countable record of years genuinely lived. A photon's lifetime, from its own personal point of view, contains none of that structure whatsoever. Birth and death occupy the exact same instant, with nothing measurable happening in between, regardless of whether that photon's journey, as measured by an outside observer, spanned 8 minutes or 14 billion years. There is no childhood, no middle, no gradual aging process for a photon to experience. There is only creation, followed immediately, from its own perspective, by destruction, with the entire vast journey in between completely invisible to the photon's own internal experience. No candles, no milestones, no accumulated years of any kind mark a photon's passage through existence. Picture stacking 100 years of a human life against a single, infinitely thin slice of time, so thin it cannot even be measured using any unit humans have ever invented. That comparison captures, in a rough way, the staggering gap separating a human lifetime from a photon's lifetime. One stretches out richly across decades, filled with sunrises, seasons, and countless ordinary days. The other collapses down to absolutely nothing, a true zero, not simply a very small number rounded down for convenience. Yet here is the strange twist worth sitting with. From an outside human point of view, watching a photon's journey unfold across billions of years, that same photon appears to live an almost unimaginably long life, far longer than any human, any civilization, or even any star could ever hope to survive. The contradiction dissolves once you remember that these two descriptions are simply answering two different questions. Ask how long the journey lasted from Earth's point of view, and the answer stretches across eons. Ask how long the journey lasted from the photon's own point of view, and the answer is always, without exception, exactly 0, no matter which star, which galaxy, or which corner of the universe that Photon originally called home. This means a photon simultaneously holds the shortest possible lifetime imaginable and, from an outside perspective, some of the longest lifetimes ever recorded in the history of the universe. Two completely true, completely valid answers existing side by side without ever contradicting each other. A human lifetime measures roughly 80 years, no matter who is doing the measuring. A photon's lifetime depends entirely on who is asking, and from where. A strange kind of flexibility built directly into the fabric of space and time itself, reserved exclusively for anything brave enough, or simply unable to avoid, travelling at the absolute speed limit of the universe, a limit no human, no spacecraft, and no measuring instrument will ever personally reach. Every star glittering across tonight's sky is delivering a message, carried across almost unimaginable distances by something that never once grew tired, never once slowed down, and never once aged a single day along the way, no matter how far that message needed to travel to finally reach you. That message is the light itself, arriving after a journey that, from its own perspective, took exactly 0 time to complete, no matter how many years, centuries, or billions of years passed according to clocks here on Earth. Every star, every faint smudge of a distant galaxy, every fleeting streak of a meteor burning up in the atmosphere, all of it represents information delivered by a messenger that experienced none of the delay separating its departure from its arrival. That messenger never rested along the way, never paused to catch its breath, and never once felt the weight of the distance it was quietly crossing. This transforms the entire night sky into something closer to an enormous, patient archive rather than a simple decoration stretched overhead. Each point of light carries a specific piece of history, frozen at the exact instant it departed, untouched and unedited during its entire journey across the emptiness of space. Some of those messages are remarkably fresh, having left their source only a handful of years ago. Others carry news from before human civilization existed at all, patiently crossing the universe for millions or even billions of years before finally arriving at exactly this moment, over your head, tonight. No filing system on Earth could ever organize an archive this vast, spanning this much time, delivered this quietly. Picture an enormous, silent postal service, delivering letters across the entire universe without ever losing a single one, without ever damaging the contents, and without the letters themselves ever aging a single moment during transit, no matter how long the delivery route happened to stretch. Every star you can see participates in that same silent delivery service, sending its own letter across space, patiently waiting for it to finally arrive at Earth, sometimes long after the sender itself has already changed dramatically or ceased to exist entirely. No postmark, no where, no evidence of the journey ever shows up on the envelope itself. This gives starlight a strange, almost paradoxical identity. It is simultaneously ancient, having crossed distances and durations that dwarf all of human history combined, and permanently, eternally new, having personally experienced none of that staggering journey at all. A beam of light leaving a star today, and a beam of light leaving that same star 10,000 years ago are, in a very real sense, exactly the same age from their own point of view, 0, regardless of how differently those two journeys eventually play out once they reach an observer somewhere across the universe. Neither beam carries any memory of waiting, since neither one ever truly waited at all. Every single star overhead tonight is quietly performing this exact same impossible trick, simultaneously ancient and newborn, delivering a message that took forever to arrive and no time at all to send. Understanding that contradiction and recognizing it as a genuine, confirmed feature of the universe, rather than a trick of language or imagination, changes forever how a simple glance upward at the night sky should feel, turning an ordinary moment outdoors into direct contact with something that has been quietly waiting to arrive since long before you were born. Step outside tonight, look up, and let your eyes settle on the very first star that catches your attention, wherever you happen to be standing. Whatever star that happens to be, you are now standing directly in the path of a beam of light that has just completed the strangest journey physics has ever described. That beam crossed an ocean of empty space, stretched across years, centuries or millennia, arriving at the exact spot where you happen to be standing, at the exact moment you happen to look up. From its own frozen point of view, that entire journey took 0 seconds. From your point of view, standing there in the dark, real years passed, while that light crossed the gap separating its home star from your own eye. No other messenger in the entire universe could have delivered that same picture any faster. You are, in this exact moment, touching something profoundly ancient and something impossibly new at the very same time. Ancient, because that light began its journey long before this moment, carrying a snapshot from a point in time you can never visit or verify any other way. New, because from the light's own perspective, its birth and its arrival at your eye happened in the exact same instant, with no delay, no aging, and no waiting whatsoever built into its own personal experience. Both descriptions are completely true at once, sitting side by side without ever cancelling each other out. Picture holding a letter written by someone who lived centuries ago, their exact words and thoughts preserved perfectly, untouched by time, arriving directly into your hands today as if no time had passed at all since it was written. Starlight delivers something remarkably similar, a direct, unedited connection reaching across time itself, carrying a piece of the past directly into your present without ever aging, fading, or changing along the way, exactly as true today as it was the instant it first departed. Every single person who has ever looked up at a clear night sky, across every culture and every era of human history, has witnessed this exact same phenomenon without necessarily realizing what they were seeing. Ancient sailors navigating by starlight, farmers marking the seasons using the position of familiar constellations, children today snapping photos of the night sky on a phone. All of them stood beneath the same ageless light, connected across centuries by beams that never once experienced the passage of time separating one observer from the next. A shepherd watching the sky thousands of years ago, and a person scrolling past a photo of that same sky tonight are, in a strange sense, sharing a single unbroken conversation with the stars. This is why light cannot grow old, anywhere in the universe, under any circumstance, no matter how far it travels, or how long that journey appears to take from an outside point of view. Speed itself protects light from ever aging, locking its personal clock permanently at 0 the instant it exists. Tonight, standing beneath a sky full of ancient, ageless messages, you are witnessing proof of one of the strangest, most thoroughly confirmed facts in all of physics, written directly across the darkness above you, patiently waiting, as it always has, for someone to simply look up and to finally understand exactly what they are seeing.